All right, welcome to part two of my talk on a survey of electrostatic global placers. You can see part one for where I talk about ePlace and replace. I'm going to quickly review what I talked about last week, just so that we're all on the same page. So FPGA placement is a complicated problem. I have an input of atom netlists, and I need to output a clustered placement. And my objectives are usually minimize wire length and critical path delay, as well as others like routability. And my constraints are atoms can only be placed in compatible cells where a path exists for each atom's connections. And a common technique to do this is analytical placement, where we solve analytical equations to place the atoms by using relaxed objective and constraints. And what that gives me is a nice globally placed solution where atoms are approximately where they need to be, but not fully legalized yet. We pass that into a full legalizer. This is something that reminisces to a packer or also an initial placement. And then finally, we do detailed placement, which while keeping ourselves within our constraints, we optimize the objectives. So last week I introduced two global placers. There is the quadratic global placers, which solve a QP problem, where we encode our objectives into this Q matrix, and we encode our constraints also into this Q matrix as well as the C matrix. Hi, Vaughn. I got started without you, so I hope that's okay. And the topic of discussion for this presentation are nonlinear global placers, which instead of constraining ourselves to a quadratic equation, we can constrain ourselves to having any differentiable objective function and any differentiable constraint function. And we can use a Lagrangian relaxation to minimize this unconstrained optimization problem using gradient descent techniques. So in this presentation, what I've been focusing on are nonlinear global placers, which represent their problem, the analytical placement problem, as an electrostatic system. So I'm just going to skip through the pros and cons. You can watch the video. So last week we talked about ePlace MS. ePlace MS, let me just see if I can find a good summary. ePlace MS tries to optimize the objective function of minimizing the half perimeter wire length, but they also need to represent the constraint function, which is the density. And the idea is, why don't we represent each of our atoms as an electrostatic force or positive charge? And all of these different atoms will feel a repulsive force from each other. And that creates these electric field looking things. And the idea is that as I increase my Lagrangian, as I increase the electrostatic force, the forces keeping the atoms together, which is trying to minimize HBWL, will be counteracted by the forces repelling them apart, and eventually they will spread enough that we can stop. And that's how electrostatic global placers tend to work in general. I also talked a little bit about fillers and DC offsets, as well as how we compute the gradient descent technique, but you can watch the previous video for that. So yeah, we then talked about replace, which builds onto this approach by taking our objective function from ePlace, the density function from ePlace, but adding on this new D local or density local, where they say this density function is specific to the bins, where each bin applies the forces on the atoms within that bin. They also added a momentum term, which will keep blocks moving the second they moved out of a very, very congested bin. And finally, they did some dynamic step size adaptation based on a initial placement, or not initial placement, excuse me, a trial placement where they run a global placement in its entirety to find these special points that it calls TP1 and TP2, which it uses to pick the step size. I know I had to rush through that, but I wanted to just give a brief summary of what we talked about last week. So in this week's presentation, what I want to talk about is our last ASIC placer for what I'm going to be talking about for these talks, which is DREAMPlace. What it does is it takes the ePlace problem and accelerates it on a GPU, but doing so in such a way that is very interesting. They cast the problem to a neural network training and then use the algorithms already built for that purpose in order to accelerate their analytical placer, which is really, really, really cool. Could someone close that door, please? Thanks, Haidar. So, DreamPlace models the placement problem as a neural network training. What does that mean? Well, they have this really excellent figure to explain it. On the left, we have neural network training, which is trying to minimize this function, which is some function with an activation plus some regularization term. And what we do is we say, if we really squint our eyes and tilt our head, what we're going to notice is that we can think of this, let me just, we can think of our wire length as the error function, which is like a loss function in neural network training. And we can think of our density as the regularization term in neural network training. And if we do that, we can notice something that, these are almost the exact same thing. And so I could use the libraries, for example, PyTorch or TensorFlow, which are already designed for optimizing the left equation, and kind of trick it into optimizing our equation. And by doing so, we can make use of all of the big improvements in AI, which have done things like, which are trying to compute exactly this by accelerating it on things like GPUs. So how do we do this? Well, we take our optimization function, which is what DreamPlace does. They actually do the ePlace and the replace work, and they make sure both of them work in the DreamPlace framework. And since we're modeling placement as neural network training, we only need to make custom ops in C++ and CUDA for the wire length and the density. Everything else we kind of get for free, that it comes from the framework. So the reason why we write it in C++ is because sometimes these neural network training tools like PyTorch give you the option to either run on C++ or on CUDA for GPU or CPU. So what they did was they wrote their C++ and parallelized it using OpenMP, and they wrote their GPU code in CUDA. So, and they also needed to define forward and backward ops for both ePlace and replace global placers. So they actually created a kernel or special op in GPU code specifically for the weighted average wire length objective, because this didn't already exist in PyTorch, for example. They also needed to write one for the electrostatic global density function. Again, this is basically just a fast Fourier transform. They also parallelized this on GPU. You can see the papers for the algorithms of how they parallelize this on GPU. I'm skipping that for now because mainly it's just the same algorithm as before, just with some tricks. And also for replace, they added an electrostatic local density function, which they also implemented on GPU. And then finally, the Nesterov's gradient descent method already existed in PyTorch, so they can actually make use of the Nesterov's method found within. So yeah, that's all they did. Now, it doesn't sound like much, but what's really important about this work is that they're leveraging all of the acceleration frameworks from other people in the neural network domain to actually accelerate their problem, which is a really genius idea, because recall from last week, the faster I can compute an iteration of my global placement, the more iterations I can do, and the better quality of a placement I can get within my time limit. So that's what's really important. So what were the results of DreamPlace? Well, what we were able to see is up to a 43 times runtime improvement over the replace algorithm on CPU. Now, and replace was parallelized to multiple threads, and we can see even then where they were able to get upwards of about 43x. Let me just double check. Yes, upwards of about 43x runtime improvement, which is a very large improvement. Now, granted, it's not exactly an apples to apples comparison because, again, this is using GPU acceleration. This one's using CPU acceleration, but it's still a massive improvement.
Read all this. So it's all compared to replace on one CPU? Yeah.
I believe so. Yeah, DreamPlace on I forget which one was TCAD and which one was DAC. I don't remember. But I believe these three are the GPU accelerated ones, and these ones are the CPU accelerated one. And 1.0 is the GPU accelerated one, using float 64. Right.
Okay, so replace is probably serial.
Uh,
And then they're doing DreamPlace with different numbers of CPUs, I think. Yeah.
So this purple bar we see up in the top left, that's serial. And this one, I believe, is 40 threads.
Yeah, but I'm guessing that's for DreamPlace on a CPU, I think.
No, this is replace.
Okay, so that's replace can be run in parallel.
Mm-hmm.
And then they go DreamPlace, and I guess the purple bar is always compared to replace one CPU?
I believe it's all the 1.0x, the baseline, I think is DreamPlace on GPU.
I see.
They said that they can actually get even more improvement by instead of using float 64 F doubles, they changed it to floats. And they got slightly more improvements, but they wanted to compare it apples to apples. This is using doubles, so this one's going to use doubles as well.
Actually, I should work that well with doubles. GPUs aren't very good at double, so.
Yeah. It's pretty interesting. So the results are very good. And they also had this really great section in the paper, which compared Nesterov's solver to atom and stochastic gradient descent, because it's as simple as just changing a single variable in their code because it's provided by PyTorch. So, and they showed the results comparing the three. They did find that Nesterov's is the best, but they had this excellent sentence in the paper that I really appreciated that basically said, although Nesterov's is the best, we tuned this replace and ePlace was tuned to run on Nesterov's method. So I'm sure with tuning, atom and stochastic gradient descent can be just as good. So they said take it with a grain of salt, but they said in the paper, the point of it was that it was that easy to just swap out those different solvers, which I think is what really announces what's so great about this paper. It makes it easier to try different analytical placement techniques. So that was, oh, yep, and demonstrates how easy it is to try different solvers. So that was DreamPlace. I know I'm going really quickly over it, and that's not to say this wasn't a great paper. It's just I'm focusing on global placement in here. And what to take away from DreamPlace on the topic of electrostatic global placement is that they accelerated it on GPUs, which made it significantly faster. Any questions on this? Cool. So what I've been talking about for the last 2 weeks has been ASIC placers, which are in our own category of their own. And what makes great FPGA analytical placers are ones that are based on the state of the art of the ASIC placers. So what we're going to be talking about are the FPGA placers that took the ideas of these ASIC placers and applied them to the domain of FPGAs. But it's not as simple as you might think. So when it comes to ASICs, their constraints are a little bit simpler. They have a continuous placement regions where atoms can be placed. Aside from some obstacles that might exist, atoms can go basically anywhere on that ASIC. However, on an FPGA, the constraints are significantly more challenging. As you can see, I have my CLB atom cannot be placed anywhere within this yellow region and nowhere within this red region. And beyond that, there are constraints within these rectangles. For example, a LUT could go here, but if LUT B happens to be in another clock domain, it can't go there, unless it's over here, in which case it can go there. So there's this complicated hierarchy of what atoms can be placed within a given tile, and that's dependent on the other atoms that are also within that tile. And it's a lot more complicated than just being on an FPGA, just being on an ASIC, which can be basically anywhere as long as it's not overlapping.
So Alex,
oh yeah,
yeah, it may be more. I think what happens is that ASIC versus FPGA placers just have a different approach to heterogeneity. So in an FPGA placer, you have all these different kinds of blocks, and then they have cracking constraints, and that's a problem. When you look at ASIC placers, they tend to have much better support for large blocks and megacells and things like that, which creates an immense problem. Now, I think these things were less far apart in the 90s because ASIC placers also back then used to address gate arrays, and they don't do that as much. So a cell-based array often gave you a heterogeneous base array, but in ASICs nowadays, everybody's standard cell, so all you have is a grid.
Thank you so much, Dan, and I think you're absolutely right. The key to FPGA analytical placement versus ASIC placement, just summarizing, is the heterogeneity. We need to be able to handle that we have different types of blocks that can go to different types of regions. So it's a discrete placement region with complex atom interactions, attractions and repulsions. So in the paper I want to talk about today that tries to tackle this problem is elfPlace, which builds off of ePlace and tries to put it onto FPGAs. And how do they handle that problem? So as an overview for elfPlace, it applies the ePlace algorithm on an FPGA, specifically the Xilinx Ultra Scale. The work doesn't have to be exactly on Xilinx Ultra Scale. You could apply it to other architectures, but it is architecture specific in that there are special magic numbers and special passes that they do to make sure it legalizes onto this particular architecture. It's not replace as far as I can tell. So they've removed that local density term that I talked about last week. And they use the weighted average HPWL objective, the same approximation from last week. They're not using the log sum exponent. And they use an electrostatic system to represent density function, similar to gradient and preconditioning, but they change the optimization problem slightly to handle this heterogeneity issue. They add a second order term to Lagrangian. They call this the augmented Lagrangian formulation. I'll explain that in a second. They have different electrostatic forces for each resource types, LUTs, flip-flops, DSPs, and RAMs. You can think of this as like having different electric fields, where the LUT field isn't interacting with the flip-flop field and so on. The interaction comes through the wire lengths. And then finally, the density penalty multiplier updates based on normalized subgradients. It's a lot of magic words, but it is kind of a simple technique. And they use instance area adjustments to encode ratability, pin density, and clustering compatibility into the objective. This is what I'm going to be covering in these slides. Oh yeah, and they also have discrete DSP and RAM legalization during the optimization. This is basically they lock down the DSP and RAMs halfway through their global placement, or maybe like 90% of the way there, and then keep doing global placement until it's done. So,
Can you go back one? I'm just gonna
Back.
back one side.
Yep.
Okay, so you got ePlace, replace have the local density function as you put in here. DREAMPlace is identical formulation to replace.
Nothing changed.
Nothing changed at all. Just moved to the GPU.
Yeah, they had to change like how the netlist was represented in data structures.
I mean, algorithm.
Yeah, but algorithmically, no, nothing
Okay.
changed.
And then ePlace, you just mentioned, okay, so it's put in, let me think about this. Okay, so elfPlace basically put in all the heterogeneous constraints you just mentioned, and you can go to the, okay, thanks to you. I think I'm caught up. Let me look at the next one again.
This one?
Yeah, so,
I'm gonna go through each of these bullet points.
okay,
So this is the optimization function used by elfPlace. This is what they're trying to minimize. We'll recognize that there's our weighted average HPWL objective. This number we want to make as small as possible. We recognize our electric potential density function. This is the same one from ePlace. But what I want you to notice is that different electrostatic forces are going on for each resource type. So that means the electrostatic forces of the LUTs is going to be different than the electrostatic forces felt by the RAMs and flip-flops and so on. Another thing you're going to notice is they have this quadratic penalty term, which they call the augmented Lagrangian formulation, where we have not only a linear term, linear density penalty, we also have a quadratic density penalty. And they have a very long argument explaining why. Do I have that in the slides? Yes, I do. So they argue so the first thing I want to talk about is why do they choose to use this augmented Lagrangian formulation? But before I even mention that, I do want to mention the real importance of this, giving each of these atoms different electric forces. Because when a LUT exists in the same location as a RAM, they don't necessarily want to push away from each other because they're trying to go for different regions in a heterogeneous FPGA. So they don't need to repel from each other. It's important that the LUTs repel from other LUTs and the RAMs repel from other RAMs. That's the key insight here, and they do different electric fields for each resource type. So I'm going to talk about the augmented Lagrangian formulation. So what they argue for in their kind of mental map of this is that when resource type S, for example, LUTs, have high potential, meaning that they're in regions of very, very high electric fields, they want the quadratic term to dominate. Now, their argument for why to do this is that it will help with conversion. And I'm going to use the term they use. They say it helps with conversion because it makes the objective more convex. I don't particularly like the term more convex because convex is a property, but it's basically just saying that it makes the problem more convex-like, so it's easier to go down the gradient. So that's what happens when there's high potential. When there's low potential, we want the linear term to dominate. And the argument for that is this is just the standard electrostatic formulation, which is what we want when there's very low overlap, when we're trying to do the last minute adjustments. So that's the argument for this augmented Lagrangian formulation. I think that's, oh yeah. And they actually were pretty honest about this. They say that they get about a 1.2% improvement in wire length over not having this quadratic term.
and this is an alternative essentially to what, it's not ePlace, it was replace.
Yes.
Their local density function.
That's
So
exactly
basically
right.
both of them decide they want something that is stronger for local attractors.
So that's exactly what
What's exactly right?
So in the replace algorithm, they had this local density term, which they added to their objective or to the constraints. Here, instead of adding that local density term, they add this quadratic term. Now, it's not exactly doing the same thing, but it achieves the same goal. When we have bins that are really, really, really dense and are really trying to push things apart, we want to push them away stronger than bins that aren't so overfilled. Is that clear?
Okay.
Yep. Any other questions on this? Because it is pretty straightforward. It doesn't change, it does change the gradient a little bit, but it's not enough to, but it's still computed using the fast Fourier transform. And they say it gives you a 1.2% improvement in wire length, which isn't a lot, but it's still interesting. And it's still something.
I don't read why an FFT works for this.
I
Figures that out. It's intuitive explanation comes.
I can show the equations. I just don't think it would be very useful for these slides.
Yeah, no, I'll work it on it.
So next up, they update the density penalty multipliers. Now notice I say multipliers, plural. So when we had just one electrostatic field, we only needed one lambda, one density penalty multiplier. But now that I have different electrostatic fields, I need to make sure that I have different lambdas for each resource types. That's because if the LUTs are almost legal, that doesn't mean that the RAMs are almost legal. If the DSP blocks are almost legal, that doesn't mean the flip-flops are almost legal. So they need the density penalty factor needs to change depending on the resource type. So they change. So we have different density multipliers per resource type, and these can have massively different scales just due to the FPGA architecture. There are more RAMs than there are LUTs, there's more LUTs than there are RAMs, for example. The RAMs are bigger though, so it's hard to really say. And we need to be careful not to overspread one resource type, which may ruin the global placement. If I only had one lambda and one thing was super dense, all the others will just start scattering, which is going to just destroy your global placement. So they initialize their lambdas to all be the same, but they use this interesting formula. So the numerator is the magnitude of the gradient of the wire length objective for the initial placement. And for this work, they use a random initial placement using standard normal distribution around the IOs. They just found that random initial placement is good enough for what they're doing. So they set the lambdas to the magnitude of the gradient of the wire length objective divided by the total potential energy of all systems, of all instances, excuse me. So it's hard to get intuition behind this, but they have said that this works very well. And this last term is just saying all initial penalty factors of all resource types are exactly the same.
I think there is an intuitive explanation for this, that neta is probably just a heuristic factor.
Yes. 10 to the power of something.
So they're normalizing it. They're basically saying take the magnitude of the gradient divided by the magnitude of the potential energy, which I think is effectively what you have in your electrostatic term.
Yes.
Right? So they're just basically, I have no idea what the magnitude of those two terms are. Let's just compute their magnitude and we'll make the lambdas proportional to that.
Yep.
Like basically, if I multiply through by the denominator, lambda times my penalty term.
I see your
is
point.
now of the same magnitude as the gradient of the wire length. And it's a scaled gradient by this neta. So now I got like some parameter that probably I can vary between 0 and 1, and I know what I'm doing.
I see. Actually, that is a great way of
We try
putting
to do
it.
the same thing in BTR all over the place, right? Like we have no idea what the magnitude of the wire length and the timing term are. We'll basically normalize each to their current magnitude and have a trade-off term. I think they're basically doing the same thing.
Thank you, Vaughn. I think that's better than I could explain it, that's for sure. So yeah, that's just how they initialize it. And then what they do is they use an approximation of what's called the subgradient to update the density penalties. Now, they say in the paper that updating these lambda terms by the subgradient is just a standard technique in optimization, where the subgradient is the current cost of the electrostatic density for this resource type. So it's just take the current cost, and that's your subgradient. But the thing that they add for this paper is they normalize it by the initial potential energy of the resource type. This just say that they say just helps it converge better, and it keeps it from getting too large. And then they have this crazy updating scheme, but to explain it, it's just basically update your lambdas in the direction of the subgradient. And this next part says, increase the step size or increase lambda faster when the quadratic term is large and slower otherwise. That's what this means. I don't want to go too in depth into the exact math of this, but this is essentially how they update the lambda terms. They set it equal to that initial lambda from the beginning. They update this using subgradients or magnitude of the subgradient. Any questions on these density penalty multipliers? I just wanted to show you guys that there is some magic going on when we update these penalties, but it's not super inconsequential. It's not inconsequential, but it's not that important. As long as you know that there are different lambdas for each electric field, and they're updated in an intelligent way based on the current, let's say, the current electrostatic forces felt by the certain type. So that is updating the density penalty multipliers. There's this last thing that they do, which is called instance area adjustments. Every so often during their global placement, they'll actually stop, look at the areas of the LUTs, the RAMs, and everything like that, and they'll actually recompute the areas and increase them or decrease them based on different objectives like routability, pin density, and clustering. The idea here is that if I find that a LUT is in a very congested region, I can increase its area to tell the other LUTs around it to stay away. Another thing is if I find that an instance in a bin that's over the pin capacity, meaning that we're using too many pins, again, I can increase the area to tell the pins to go away. And then I can also say, if this is in an incompatible bin, I can also increase its area again, or I think decrease the area in this case, try and move it into another bin. And the idea is that they will then adjust the physical and filler instance areas to apply these constraints into the problem. It's a little bit of a cheat, I would say, to try and get this to work so you can have both routability, pin density, and clusterability, let's say, or the ability to legalize into this problem. But they need to update the density multipliers at this point, because once you've changed the areas of these instances, you've changed your electrostatic forces, so the lambdas are now completely wrong. So they recompute the density multipliers, the lambdas from the previous slide. So so that's about it for what they do. They just use the area of these instances to enforce these objectives.
Yeah, so they're figuring out how much spreading they want. So the first two terms on the left are both measures of congestion.
Mm-hmm.
So RESA is a technique that basically smears out the wiring across the bounding box of a net.
Right.
So it tends to take into account sort of medium and large scale wiring estimates, right? That doesn't know how you actually route this, but it says you'll route within your bounding box. So just smear out the amount of wiring evenly over the bounding box. Let's add all that up and see if we're going to overuse things. And then you can get local congestion where you just have lots of pins in a certain spot. It can be hard to make everything connect together. So the second term is a very localized congestion.
Mm-hmm.
So I think the first two are basically, I have estimates of congestion below your area if you're in a congested region.
Pretty much. And I'll get into when this occurs. This occurs when they're basically almost done. So the global placement is getting close to convergence. It then updates the areas, gets close to convergence, updates the areas, and does this again and again until of a certain stopping criterion. So this is the result of the optimization function. This is like probably the most famous picture from this paper. The top is very early on during global placement when we can see that the atoms want to be in these really dense regions because their wire lengths are telling them to get really close together. And the electrostatic forces are pushing them away, and it looks like nail filings in a magnetic field, which is kind of cool. And then down here, this is what they claim happens towards the end, before legalization of anything. So they didn't even lock down the DSP or RAMs at this point. And as you can see, things are getting really close to legality here. We can see these nice long strips of DSPs, nice long strips of RAMs, and all this sea of LUTs. Now, I had a question when I read this paper. This picture on the bottom doesn't make sense based on the formulation that I've talked about so far. Because based on this formulation, how do I get these nice straight lines? Because that doesn't really make sense from the way I've been describing things so far. I thought at first it was some complex interaction with the fillers, and maybe they just got really lucky and things just fell into these local minimum. But as I read some of their future papers, which I will talk about, later, I think there's a hidden trick going on they don't mention in their paper. One question I had from the previous image is, it should not be possible with just fillers and primitives having negative charges that things would create those nice long strips. There needs to be some force pulling the primitives to their valid sites or pushing them away from invalid sites. So from reading other papers, I think what they did is that legal sites for each research type have fixed negative charges, which attract the positive charges of that type. So for example, all LUTs will feel an attraction to valid LUT sites, and that's what I think is going on. This would attract each of the primitives to their respective sites. Now, and this could explain the structures in the previous picture. I could not find anywhere in the paper that even hinted at this, but nowhere in the paper said that they didn't do this.
But that's not. You
So
can apply that to anything.
you can apply it to anything, but then in their 2024 FCCM paper, they mentioned this is something that they do. So as I was reading the 2024 FCCM paper and I read that line, I said, they don't do that. And then I looked at the paper and I said, they don't do that. Then I looked back at their FCCM paper and I was like, wait a minute, they totally do that. So this might explain how they got like some of their secret sauce and how they get things to actually converge well. Because how else would they be able to get things to go to the valid sites? It just doesn't really add up, unless maybe this area adjustment scheme is somehow applying to this, but I really doubt it. So I believe that, for example, all these red instances feel an attraction to lines of positive charges here, here, and here.
Do they have any legalizer in the middle of between those two pictures?
No.
So they're just solving over and over again and adjusting the density, like adjusting the areas and
Yes.
solving again and again.
Technically, you can argue this third rectangle here is a type of legalizer, but they don't have formal legalization.
But that only changes its area if it's in the wrong spot.
Yes.
You also mentioned they have something that assigns you to DSP, I think a matching algorithm or something, that assigns you to DSP columns and RAM columns.
That happens after this picture. They made it clear this picture happened just before.
So this is only solving the solver over and over again. Yeah, you're right. It seems
There's something magical going on here.
something's going on. Okay.
Completely agreed. So I want to be clear, this is my slide. I wrote this as kind of like while I was reading the paper, I thought that was weird. And then as I was reading other papers, I realized this is what they're probably doing. You could go, the elfPlace paper, I don't think is open source, but DREAMPlace is. And if someone wants to dig into DREAMPlace and check, or DREAMPlace FPGA, they can do it. I just haven't done it.
elfPlace should be open source now.
They should be it now. It didn't say it in the paper. And I also
The
tried.
FCCM one, I think said it would be open source. So hopefully it is now, but I haven't checked either.
I did go through the DREAMPlace FPGA code. It was too big. I didn't have time. So I just thought it was interesting. And also, this is kind of those little tricks that analytic placers have to do sometimes, because heterogeneity is a really hard problem to deal with. And I think assigning these to positive charges are just a really natural way of getting an attraction to valid site regions. So this is the overall flow of elfPlace. We read in an initial placement. Again, this is just Gaussian normal place atoms near IO block, fixed IOs. They randomly insert some fillers, which are the same fillers I talked about last week in ePlace. They initialize their lambdas, and then they compute the gradient. They do Nesterovs. They update the gradient, and then they check, is the overlap of the LUTs and overlap of the flip-flops greater than 15%? If yes, keep going. If we are starting to converge on the LUTs and flip-flops, we do an area adjustment, and then we decrease the lambda because the areas have changed, and we continue. If the last time we did the area adjustment, we didn't change the area by all that much, we then go down and we check, okay, is the overlap now 10% and the DSP and RAMs are mostly legal? If yes, we're going to lock down the DSP and RAMs. They use a min cost flow to legalize their DSP and RAMs. And then once they're locked down, they lock down the DSPs and RAMs. They then do the global placement again. This time they keep going until LUTs and flip-flops are nice and happy. And
possibly your previous picture came after they locked down the DSPs and RAMs.
They said very specifically in the paper that this was just before. The whole so what of this picture was that, hey, look, this is what our global placer can do.
Yeah, before they locked it down.
Yeah.
Okay.
So that's why I'm kind of nagging on it a little bit.
Yeah, interesting.
Yep, and then finally they have this final clustering, legalization, and detailed placement, which happens later. But again, focus of this presentation is global placement. So locks down the DSP and RAM blocks towards the end of the flow. So a summary of elfPlace. The objective is the weighted average HPWL approximation. It's the exact same as ePlace. The constraint is the ePlace electrostatic density function per resource type. Again, we're trying to get heterogeneity here. And it uses an augmented Lagrangian to add quadratic terms to improve convergence. And they may add fixed negative charges for compatible sites, but again, they don't make that obvious. And the optimizer, it's the exact same as ePlace. It's the Nestorov's method plus the fancy stuff I talked about last week, which you can review. And it updates the density penalty multipliers based on the current potential energy. It updates the area of atoms to encode other objectives into the optimization. And they legalize and lock down the DSP and RAMs, those really big blocks towards the end of the flow, since we don't want those moving around, since they can have huge effects on my final global placement. And the big so what of this is that they apply the electrostatic formulation from ePlace to FPGA, modifying it to meet the complex constraints of FPGAs, which is what I think great analytical placers do. They take an ASIC analytical placer that works extremely well, and they modify it to meet the complex constraints of FPGAs. And so they perform discrete legalization and updates every so often to meet the FPGA legalization requirement. That's the area adjustments, that's locking down the DSPs and RAMs, as well as treating things differently for electrostatic forces. So that is a elfPlace. What do people think? Is everyone okay? As I said, ePlace was the hard one. Now we know ePlace, I don't need to cover all that again, so elfPlace just gets a little easier to explain. Okay, so that was elfPlace. Now we talk about another paper that actually came out on the same month as elfPlace. So these were actually at different conferences, but I think they were about a week and a half apart from each other. This is a marry between DREAMPlace and elfPlace. Now I didn't make this clear in my slides before. elfPlace had GPU acceleration. They made it clear in their paper they did have GPU acceleration. So these slides are not exact. So that's why I actually said elfPlace plus DREAMPlace here. This, they then put elfPlace into the DREAMPlace framework and use the GPU kernels they've already written from elfPlace to put it into DREAMPlace FPGA. So the DREAMPlace FPGA overview is that they implemented elfPlace into the DREAMPlace framework by taking their GPU accelerated kernels and adding them as ops into the PyTorch framework they added. They added new PyTorch operators and C++ CUDA kernels, and they have this really handy picture from the paper which says exactly what they did. So they added a new placement API to make it easier to work with. They added their density terms that we just talked about, one for each data type, one for each flip-flop, and so on. They added their clustering aware instance area adjustments. The routing congestion already existed from ePlace. And then they had DSP and RAM legalization as a new operator. And then finally, they were able to reuse things like Nestorov's optimizer and the wire length one, because that was actually from the original DREAMPlace paper. And yeah, so that's what they did in this paper. The reason I bring up this paper is because future papers talk about this work as being like the elfPlace work. And this is the one that people tend to compare against. And this is also the open source elfPlace is in here. So that's why I know that DREAMPlace FPGA is open source because I saw the code. I don't know if elfPlace from that paper exactly is there.
Yeah, so that I'm not sure about. Maybe DREAMPlace FPGA.
I think they were one in the same, I'm not sure. But anyways, so the results of this, they were 19% faster GPU runtime for global placement over elfPlace, which also had GPU acceleration. So this is an apples to apples comparison. And this includes parsing the benchmarks and writing out the placement solution. But the overall placement flow of DREAMPlace FPGA was 1.2% slower for over elfPlace. And the reason why was because they actually noted that there was an increased data movement runtime caused by creating intermediate databases, which were managed by Python. basically the fact they were using Python and using this higher level API required them to copy things more often, which is usually what happens when you abstract things more and more. The more you abstract things, the more you'll have to copy intermediate data into intermediate buffers that you could have optimized away if you completely written the flow from scratch, but they're just basically showing that they're losing a little bit from having to read all this data movement. And finally, using DREAMPlace FPGA provides an easier interface to develop and modify the placement algorithm. It's the same objective as DREAMPlace was originally. Now that we have this, you can now add more analytical placement algorithms into this framework, and you can compare them effectively. So that was basically it for DREAMPlace FPGA. That was the contribution. It was just that they've added the elfPlace framework into DREAMPlace. Any questions on that? Yes, I get to get to the last paper. If we run out of time, we run out of time. I have 7 minutes to do this, but I wanted to talk about FPlace's FCCM paper from 2024, which took the DREAMPlace FPGA, which is GPU accelerated elfPlace, and added a timing term, basically making it timing oriented. How they did this was that they built off the DREAMPlace FPGA work or elfPlace algorithm. They added a congestion-aware timing term to the actually, that's not correct, to the function, to the optimization function. That's actually important to say. Each timing arc is weighted. This is similar to net weighting, but instead of weighting the whole net the same way, they weight different connections, different weights. And they need to update the timing every so often because as the placement moves, you need to re-update the timing. This becomes a big problem. And they update the Packer legalizer with a timing objective. However, I'm not discussing this in this presentation. I'm focusing on the global placement here. So here is our optimization function for elfPlace's FCCM 2024 paper. We recognize our weighted average HPWL objective. It's never going anywhere. We have our electrostatic density function from before, ePlace. We have our density penalty factor, and now we have the new things on the right.
And that still has the linear and quadratic terms.
Yes, everything's exactly the same as elfPlace. But now we have this new thing. What we have is a weighted average wire length of timing arc. Now, when I read the paper originally, this confused the hell out of me. What is weighted average wire length? It's this same exponential trick they were doing before. So this is just that approximation of HPWL that I've been talking about for the last few weeks. And then they take, for each connection in the net, they multiply their weighted average wire length by a timing arc weight, which is proportional to the criticality. And then they have this extra timing penalty factor similar to the density penalty factor. This, I find, this timing penalty factor of beta to be the strangest part of this paper, because that means that they make timing a constraint, not an objective.
Think of it as you can think of it as a weighting term to that.
Beta changes. As the iteration changes, beta increases.
It's not irrational.
It's not irrational.
Because timing is less understood at first. You can just try to optimize wiring, saying I'm optimizing everybody, and then later on you can focus more on timing. So
well,
I don't think of it necessarily as that means it's a constraint. You can also think of it as an objective factor.
You can. It's just the fact that beta always increases is why I think that it's treated as a constraint. It doesn't go to infinity, though. It seems to be linearly increasing.
Okay, so basically you're saying that the beta summation term is another Lagrangian. Beta is being treated as a lambda. And then because it's a constraint, what does that mean? Once the timing is achieved, there's no more, that will never be, normally when you're timing driven, you over optimize the timing. In this case, it won't do that?
I don't know. It doesn't say in the paper. It's just that they added this term with this beta. I personally would have just kept this as a constant, some constant times this term, because then it would just be your objective is minimize the timing the best you can, and then you spread things out while trying to keep that timing low. That's how I would have envisioned this work. And so I just found it strange that they were increasing beta over time, because I don't know why you'd want your timing to be less important early on and get more and more important over time.
It's a fairly common technique, right? Early on, you don't know much about timing.
Okay.
And if you try to optimize all your wiring, you do approximately the right thing for everybody. And later on, you can focus more
Yeah, I agree with Vaughn. I mean, I think both lambda and beta, both your congestion picture and your timing picture are going to get better over time, and that provides a rationale for altering lambda and beta.
That makes sense. Gotcha. I just found it strange because normally you would do net weighting within the objective term for the quadratic places, for example. So that's why this is actually a pretty big difference than what people would do in like a quadratic placer with net weighting.
Well, those timing arc weights will be much less stable. They're doing a retiming analysis once in a while, like you
Yes.
just said. And from that, they're extracting these net weights. Unless they start saying I've met timing and I drive the timing arc weights to zero, I don't think it's difficult to think of this as a Lagrangian where you're gonna say it's legal.
Correct.
Because unless you drive all the criticalities to zero, which you could do if you meet timing, but otherwise it's never gonna go to zero.
You're right. And there is a difference here. This lambda gets really, really, really large. This beta is linear with the number of iterations. So it's not going to get massive, but it's still getting larger over the course of a global placement.
Yeah.
But I think also the problem here is our mental thinking is sticky. I mean, we have a habit of like running benchmarks and we let the timing optimization go as far as possible. And we're used to doing that.
Right.
But most of the time when you're optimizing a design, timing is simply a constraint to meet. Once you've gotten the 400 megahertz or the 200 megahertz you want, the customer is not interested in going beyond that. Just like once you've achieved packability or you've achieved that it fits in the design and there are no overlaps, you're not interested in adding additional spaces, right?
That's a really fair point. I like that actually. That's a really,
I think it's attitude here, and what we've been doing for decades affecting this.
So the other thing that's interesting here, and it's different from what we do in BTR, but it makes sense why they do it, is they're implicitly assuming delay is a linear function of distance, right? So you've got your weighting an arc, and then you've got WT, like the source, that presumably the source to destination distance, right?
Sync to drain, yes. One connection.
Was it probably source to, it is probably done from
I
the source
have a
of the
picture.
net.
I have a picture here.
Yeah,
The
so
driver to
from
the load.
driver to the sink. So and because they're multiplying that by the wire length, I mean, it's reasonable in line with placer. They're assuming a linear function with distance, which is approximately true, but not quite true in an FPGA. It's more true than ASIC.
They do something more than just distance here, because how they compute the delay actually encodes some congestion information. I'll get to that in a second.
We'll go back though, but there's two different terms there. There's like a timing arc weight, which they can do all sorts of stuff to compute a delay when they're calculating that. But that WT, unless they do something special for that, that is a wire length.
That is just a wire length, yes. You can think of it as like the HPWL going from here to one of these three.
Yeah, so that is implicitly, essentially, like that's guessing delay is a linear function of distance.
Ah, I see your point.
The weighting term can be thrown through the timing analyzer. It doesn't have to make that assumption.
So yeah, and so this is what timing arcs are according to this paper. I'm gonna go 5 minutes over. Is that okay, Vaughn?
I'm gonna have to take off, but that's fine. So
okay, I think I'm gonna go. If are people okay with just? I got 5 more minutes. Awesome. This will be recorded. So what are timing arcs? Well, normally when you if you're doing, for example, net weighting, you would want to get the most critical arc inside of a net, which in this case would be negative 100 picoseconds. And so, but what they argue in the paper is that this is, instead of weighting the entire net by the worst slack of any connection, if I had a really bad connection, I should try to bring that one in. I don't need to bring all the others inwards, if that makes sense. So I want to weight each of these individually to try and bring if this one has a really bad negative slack, bring load pin 1 closer. Don't bring the other two closer as well. They don't need to be. So that's the key insight from this work. And how they weight the timing arcs is using this equation. They take the criticality of the timing arc and raise it to some criticality exponent, which is an empirical value they just set to 9. And then the criticality is just 0 if the slack is positive, which means there is no timing closure issue. And then 1 minus the slack divided by the max path delay of the current placement. And that's if the slack is negative. This is basically just a number from 0 to 1 saying 1, this is the most critical net, and 0, this is the least critical net.
Okay, and can Dmax, does that come over the set of paths that includes paths not currently meeting timing, or is Dmax directly determined by the clock period?
I believe it is, I'm actually not sure. They just said it was the max path delay of the current placement. So they found the largest, I think it's the largest slack value.
Dmax is the most negative slack value?
I believe so.
Okay.
So that's how they calculate that weighting term. It's just proportional to the criticality with some exponential value. How they do static timing analysis is actually very interesting. They perform the static timing analysis forward and backward steps using a timing graph. So they
Right.
use this timing graph to compute the slack, and they use the current placement to approximate the delay of wires, because as you're farther apart, the delay will change. So they say that delay is equal to tau times the base delay plus the congestion delay. So base delay is due to the propagation of signals along a wire, and the congestion delay is the delay due to congestion, having to route wires around congested regions. And they include that in their delay calculation. And finally, tau is just a penalty factor for high fan-out nets. So I think they said 1,000. So if a net has higher than 1,000 pins, it will be given 1.5, 1 otherwise. So that's how they compute delay within their timing graph. But I want to look at these two terms, both base and congestion. So the base delay calculation, they actually pull the data from Vivado. So from Vivado, they say get net delays, which gives them this information. From the center of the chip, what is the delay by going 40 tiles to the right and 40 tiles up, for example, and so on. And what they recognized in this paper is that when they pulled this data in, they can do a linear approximation to this equation to actually get to compute this base delay. And all this really is just take your delta x multiplied by some constant, take delta y multiplied by some constant plus some constant. And what they do is they do curve fitting to match the data they pull in to this linear approximation, which they use to compute delay. So that's the base delay. The congestion delay is a little bit more complicated, but the idea is that I have these empirical constants to compute basically a weighted sum between the average route utilization of the connection and the average pin utilization of a connection. And where we estimate your pin, and how to read this is just, I look over a region of tiles, sum up their route utilizations for each tile, and divide by the area that I've summed over. And same thing for the pin utilization. And they estimate these two terms using Rudy, which is, you can read, I don't want to get too into this presentation already got very long.
This is really bizarre.
It's a little bit, I agree. And then
So they're taking congestion information and then they're putting it into the timing, the timing information path that's affecting the algorithm. But while they're doing the optimization, does congestion play any other role other than through this?
I don't believe so. Not as far as I remember.
That's very strange.
They are using elfPlace, and I believe they're doing that area adjustment.
Okay, so here's the problem in my mind. You can have congested regions which are not timing critical.
Oh yeah.
And I believe that this would fail on that.
Huh. Yeah. Yeah, you're absolutely right, because they're not timing critical, but then it will still give it a larger delay. And then that would actually make you want to, well, it'll make it want to spread it out. Still.
Well, the thing is, if it's tracking wires and pins through some other mechanism, and that's making it into a different electrostatic term, that's fine.
Mm-hmm.
But if you're taking congestion information and only bringing it in through the same mechanism used for timing, okay?
Mm-hmm.
In other words, the Lagrangian, which is controlled by the beta, right?
Mm-hmm.
So then what happens if, all the timing is groovy? We know if the timing is groovy, if slack is positive, all those timing terms go to 0.
You're right.
Are we doing some weird thing? Are they going to do some weird thing where if the congestion is bad, they pretend the timing is bad and that's how they get a response? In my experience, having an insufficient number of reactive dimensions, which then forces you to have one dimension react when another dimension should have been reacting, causes confusion and obscures the objective.
Yeah, I'm thinking about it, and I do know that routing utilization and pin utilization do come from that area adjustment because this is built off of elfPlace, but that is the only place as far as I'm aware.
Okay.
It's a really good point. And also, because we have these terms here, which is proportional, well, yeah, exactly. So I just want to quickly get to the overall flow just so I can say I got somewhat on time. So for the overall flow, this is what it looks like. The timing graph is built at the start of global placement. Timings are updated every so often, and placement changes lead to delay changes. The timing engine is entirely on the CPU, and the global optimization is the same as elfPlace, so it's on the GPU. Now, this is me foreshadowing the next slide. The timing engine is completely computed on the CPU, whereas global placement is on the GPU. So we can guess what's going to happen here. So, mhm. And the global optimizer is the same as elfPlace, so it's including the new timing term and it's computed on the GPU. So here's the slide I was alluding to. This is the cost of having a timing engine that updates every so often. What we can see here is global placement takes up 87.7% of the overall time of placement. That includes legalization. And the timing engine itself, which is the building the timing graph and updating the timing, takes up 97% of global placement runtime. This is because this others is your Nesterov's method. It's your computing the gradient, which usually takes the most amount of time. So what this is showing us is that not having this GPU accelerated can really hurt your runtime, but accelerating timing graphs using GPUs is a hard problem. So it just shows like the cost of having these timing engines can be quite high. So here's the summary of elfPlace FCCM 2024. Its objective is the same as elfPlace, weighted average HPWL. Its constraints is ePlace electrostatic density function per resource type, same as elfPlace. It constrains that we have a small wire length of timing critical connections, small wire length for timing critical connections. And the optimizer is the same as elfPlace. And they add timing term to the optimization function of elfPlace. And it's added as a constraint instead of an objective, which, as we discussed before, maybe there's a benefit to that, maybe there isn't, but it seems to be a pretty common technique. They try to use an accurate model for timing, and they get the base delays from Vivado. They take into account delay due to congestion, but this requires the timing engine, which makes up most of the runtime, like 97% of global placement, which is a lot. So that was all of the electrostatic global placers that I discussed. I believe there's quite a few more, but these are the ones that I wanted to focus on because they really show, first of all, ePlace introduces the whole idea of electrostatic global placement, but then elfPlace takes that formulation and applies it to heterogeneous FPGAs, and it really well shows the challenges that comes with that. So here are the references for all the papers that I discussed for ePlace, REAMPlace, DREAMPlace, elfPlace, DREAMPlace FPGA, and elfPlace FCCM 2024. All of these papers are basically the papers that introduce the respective placers, except for ePlace. I chose to use the ePlace MS paper because for mixed-sized macros, I just found that paper to be a better summary of the overall work, and I just enjoyed the paper. So that's all of the papers that I discussed. So thank you all so much for listening to these very hectic 2 weeks. I'm so sorry for going a little over. Let me know if there's any questions. Sweet. I'm gonna stop the recording. Cool.